Lesson 5.6, continued optimization. The last example that I did, I was watching, and I had gotten, for this one, I had gotten r was equal to the cube root of 20 over pi, and then I went back to find h, and my h was equivalent to 40 over pi r squared. And on the last one, I forgot to put the square right there. I forgot that square, okay? So you might want to go back and just fix that. The numbers were right. You still get 3.707 inches for the height. I just didn't write it down for some reason. So I wanted to make sure you saw that. And then the can measures r to be approximately 1.853 inches, and the height approximately 3.707 inches, with volume 40 cubic inches. And then I put of soda. Since surface area prime at 1.853 equals 0, and surface area prime of r changes from negative to positive at that value. Okay, I didn't write that down. I didn't know if you needed it, but I thought, well, I'll just talk about that since I saw that mistake. Okay, example number 5. Which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So what we want to be looking at is, is that the closest from the point to that function? Or is this one the closest? Or is this the closest? Or is this the closest? Like, you just don't know. Probably not something down here though, right? That's further. But it's probably up here somewhere. So we're going to choose just this point and just choose one point on your function. It's an xy point on your function, but since your function is y equals 4 minus x squared, we're going to call this point x comma 4 minus x squared, okay, because that is our y. And we're going to call this our distance from here to here. This is our distance. And we want to minimize the distance, d. Okay, because it said the closest point. That means we want to minimize that distance. So we need a distance equation. So distance equation, we're going to use the distance formula, square root of, because our 2 points are 0, 2, and x, 4 minus x squared. So y2 minus y1, so 4 minus x squared minus 2 squared plus x minus 0 squared. That's going to be our distance using the distance formula. So this is going to be 2 minus x squared squared plus x squared. This is going to be 4 minus 4x squared plus x to the 4th plus x squared. And so I'm going to put my x to the 4th first. Combine my like terms, I get negative 3x squared plus 4. Okay, so This is the equation that we want to minimize. This is what we're minimizing. We're minimizing the distance, so therefore this is what we're taking the derivative of. And had I left this xy, we would have had to put that y back in, that 4 minus x squared back in. But here we've got two unknowns. It's perfect. We can take our derivative, and this would be d prime of x is equal to, I would bring the 1/2 down, times x to the 4th minus 3x squared plus 4 to the negative 1/2, and then times the derivative of that, 4x cubed minus 6x. And then I want to write this 4x cubed minus 6x over 2 times the square root of x to the 4th minus 3x squared plus 4. And I see that I can factor a 2 out of this numerator, and then it will cancel with the 2 that I have here in the denominator. And so my derivative equation becomes 2x cubed minus 3x over the square root of x to the 4th minus 3x squared plus 4. So now I want to see what makes that 0. So I'm going to say whatever makes it 0 will make my numerator 0. That's how I get my 0. And then I notice that there is an x that can be factored out. So now x equals 0 is one solution. 2x squared minus 3 equals 0. 2x squared equals 3. X squared equals 3/2. X equals plus or minus the square root of 3/2. So you have 3 critical points. You have 0, you've got the negative square root of 3/2, and you've got the positive square root of 3/2. And we would be looking at the sign of d prime of x. That's why I put that there. And if I put a value less than negative square root of 3/2 in to my derivative, I got a negative. If I put one in that is between negative square root of 3/2 and 0, I get a positive value. If I put a number in between 0 and the square root of 3/2, I get a negative value. And if I put in a number that's greater than the square root of 3/2, I get a positive value. So you can see that we have a min here going from negative to positive by the first derivative test. We have a max here, and we have a min here. So since I'm trying to minimize the distance, the two that I would like to look at are the negative square root of 3/2 and the positive square root of 3/2. Those are the 2 points that I would like to find their y values, because it's asking for which points. So I'm going to go back to my original, y equals 4 minus x squared, and I'm going to put in my negative square root of 3/2 squared, and I get 4 minus, I square the negative, I get positive. I square the square root of 3/2, I get 3/2. So this is going to be 8/2 minus 3/2, which is 5/2. And then when you do the same thing with a positive, so if I just change that to a positive, I'm going to get the exact same number, because when I square it, I get the exact same number. So these are your points. This doesn't tell you what the distance is. If you wanted to find that out, you'd go back to your simplified distance equation. Square root of 3/2 to the 4th, put that square root of 3/2 in, minus 3 times square root of 3/2 to the 2nd plus 4. That would give you your the actual distance that is the minimum. So this would give you that minimum distance that if they would have asked for that. They didn't ask for it, so I'm not going to worry about it, but that's what you would have, if they would have asked it differently. But this particular problem said which points are the closest, and so those are your 2 points that would be equidistant from that point 0, 2. Okay, so now methods and conditions for justification. By the way, on this one, I said by the first derivative test, by the first derivative test, why did I put G? Sorry. D prime of X went from negative to positive at x equals square root of 3/2 and x equals negative square root of 3/2, and thus gave us where our minimum distance was located. Okay? All right. So now, this next one. Oh, the methods and conditions for justification. Method 1, use extreme value theorem when given endpoints. This method requires finite endpoints and a continuous function over the relative interval. Method 2, modified version of the first derivative test for relative extrema. Use this method when you don't have both endpoints at a closed interval, but you have a half open interval or open interval. This method requires a continuous function. Method 3, modified version of the second derivative test for relative extrema. Use this method when the second derivative is easy to obtain. So I could have used the second derivative test on here, but I felt like our first derivative, which we had right here, was just a little complicated to do the second derivative of. So I went ahead and used the first derivative test to justify our minimum on that last example. It is important to show the test works for all values in the relative domain to guarantee a global argument rather than a local extrema. So if they're asking for global, okay? Example number 6, there is a mistake on example number 6. I want to point that out to you. This rate of the row was supposed to be 3, and the rate of the walk was supposed to be 5. Okay, so please change that on your paper before we get started. And it says, suppose your house is situated on a straight shoreline. So here's your house right here on a straight shoreline. Here's your straight shoreline. You can row out 2 miles from the nearest point on the shoreline. So here's your rowing out 2 miles from the nearest point on the shoreline, and then row 6 miles down the beach each day before school. So basically, you row out 2 miles here, right? And so this is like kind of like your starting point. And what you have, I'm going to do this in a different color. Oops. What you have is you could row straight there, okay, and not walk at all. So that's one situation that you have. Or you could row to some point, who knows which point it'll be, and then let's do a different color, and then walk the rest of the way, okay? So what we're going to be looking at here is this would be the distance of your walk. This right here is going to be the distance of your row. So D sub W, we said, was distance of the walk, and D sub R, we said, was distance of the row. Because you're basically rowing your boat to a certain point on the shore right here. And it's going to be a certain distance from you're 2 miles out. You're perpendicular 2 miles out where you started. We're going to call that x. So you're gonna row a certain mile, portion of a mile probably, away from that perpendicular 2 miles out. What would be left here would be your 6 minus x, because that whole thing is 6 miles. Now, it tells you can row at a rate of 3 miles per hour. That's the rate of your row, okay? So R sub W is the rate of your row. We said that was 3 miles per hour, R sub R. R sub W is the rate of your walk, and that's 5 miles per hour. And it says, what is the least amount of time? Look at that, guys. The least amount of time. You're going to minimize time. You want to minimize a time equation. And how far from the house will you beach your kayak? So that we're going to have to come back and find. That's going to be our 6 minus x that we're going to have to come back and find, because the way we've got it situated, how far from the house do we beach our kayak? They're talking about the distance from here. They're talking about our distance from the house to where we beach our kayak. Okay, so we're going to have to figure out what that 6 minus x is. Okay, because I put the other x over here. We could have done that the opposite. You could have made this one over here x, and this one over here 6 minus x. But I don't know. I already wrote it, so I'm going to leave it. We just have to remember that that is the other question that they're asking us. How far from your house will you beach your kayak? So we're going to have to answer both questions. Okay, so now we don't have a time equation. We're trying to minimize time. So our time equation is going to be our time of our walk plus the time of our row. Well, we're going to row first, but I put walk first, sorry. And remember that distance equals rate times time. Okay, that's a formula that you've known since 6th grade. So the distance of the walk equals the rate of the walk times the time of the walk. The distance of the row equals the rate of the row times the time of the row. So if I wanted to solve for T sub W, I would just divide by R sub W on both sides. So I'd have D sub W divided by R sub W. If I wanted to solve the second equation for a T sub R, I would divide by R sub R on both sides. I would have D sub R divided by R sub R. So we could make our T sub W, which is the time of the walk, the distance of the walk, divided by 5. And we could make our time of the row, the distance of the row, divided by 3. Okay? So now, I would like to get a relationship here for x, for both d sub w and d sub r, because I would like this total time to be in terms of x. Well, I know my d sub w is 6 minus x, right? So my t sub w is going to be 6 minus x over 5. My d sub r, I'm going to have to use the Pythagorean theorem to calculate. So for that one, I'm going to say d sub r squared is equal to 2 squared plus x squared. So my d sub r is the square root of 4 plus x squared. So over here, the square root of 4 plus x squared over 3 is going to be my t sub r. Okay, this is the time equation that we want to minimize because we want the least amount of time, because you have to go to school. They're doing it before school. Okay, so let's go ahead and take that t equation and make it a little bit nicer. Oh my goodness, come on. Come on, come on, come on. Let's start working. There it goes. So t equals 6/5 minus 1/5 x. I just, split that up. Plus, I'm going to make this 1/3 times 4 plus x squared to the 1/2. Okay, because I'm getting ready to take the derivative of that. So I want to take the derivative t prime of x for my total time. The derivative of 6/5 is 0. The derivative of negative 1/5 x is negative 1/5. I'm going to bring the 1/2 down times the 1/3, giving me 1/6 times 4 plus x squared to the negative 1/2 times the derivative of 4 plus x squared. So negative 1/5 plus 2x over 6 times the square root of 4 plus x squared. And I'm going to divide by 2, I get 1. Divide by 2, I get 3. So this is going to be negative 1/5 plus x over 3 times the square root of 4 plus x squared. So my common denominator here is going to be 15 times the square root of 4 plus x squared. So this would have to get multiplied by 3 times the square root of 4 plus x squared. And this one would have to get multiplied by 5. And so there's my t prime of x. This is what I want to find my 0 for. So I want to find my critical point. 5x minus 3 times the square root of 4 plus x squared. I'm going to bring that negative over, add that to both sides, divide by 3, and then square both sides. So 25 over 9 x squared. Then we will add like terms. So I'm going to subtract, and I would subtract 9/9 x squared. That's still subtracting 1 x squared from both sides. It's just I changed my 1. That's going to give me 16/9 x squared. And then I'm going to multiply by 9/16. Divide by 4, I get 1. Divide by 4, I get 4. These all go away. So I end up with x squared equals 9/4. I take the square root of both sides. X equals 3/2. Now, I didn't do plus or minus because I'm talking about distance here. Okay, so that's 3/2 of a mile. So let's go back. I mean, we probably should make sure that's a minimum, right? So if I put 3/2 here and I look at what my t prime of x is doing, if I put a 1 in for x, I'm going to get, let's see, where is my, okay, so I'm going to get negative 3 times the square root of 5 plus 5. And if I put that in my calculator, it gives me a negative value. And then if I put, let's say, a 2 in, I end up getting a positive value. So that is a minimum. Okay, and you can check that on your calculator, please. And so now let's go back. It says what is the least amount of time, okay? The least amount of time required to reach your house. Well, I just found my x, and I'm going to redo my time equation now. My time equation was 6 minus, and then I'm going to put my x in, all over 5, plus the square root of 4 plus, I'm going to put my x in, squared, over 3. So this is going to be 9 halves, right? Because I've got 12 minus 3 is 9 halves. Division by 5 is multiplication by 1/5. So this is going to be 9/10 plus, and this is going to be the square root of 4 plus 9/4. So that's 16 plus 9 is going to be the square root of 25/4, which is 5 halves. So multiply by 5 over 5 so that I can add them together. I get 25 plus 9 is 34/10. And that's going to be miles per hour, so that's going to be hours. So 17/5 of an hour. Which would be let's see, let me make sure I did that right. 12 minus 3 is 9 halves, and division by 5 is multiplication by 1 over 5, so 9 times 1 over 2 times 5. This would be 9/4, so this would be 16 plus 9 is 25/4. Square root of 25 is 5, square root of 4 is 2. 2 times 5 is 10. Um, 17/5 of an hour. Okay. And so now it says, how far from the house will you beach your kayak? We have to take 6 minus 3 halves because that's going to give us how far from the house. So that was 12 halves minus 3 halves, 9 halves, so 4.5 miles from the house is where you beached your kayak. So least amount of time was our t of 3 halves, and our how far down the shoreline from the house. How far from the house will you beach your kayak? That would have been, since our x was here, this was our 1.5 miles, so this was our 4.5 miles. So it was 4.5 miles away from the house that we beached our kayak. I'm going to put kayak beached 4.5 miles from the house. Okay. All right. So now, example number 7. Just in case, found a 4-foot piece of wire left on a construction site. He is learning about optimization in calculus and wants to cut the wire to create a circle and a square. How much of the wire should be used for each shape in order to maximize the total area? Okay. So for this one, he's got this 4-foot piece of wire, okay? And he wants to cut it to create a circle and a square. Okay? So we're going to say that this is an x by x square. We're going to say that this circle has a radius of r. And so since the wire, when it's cut, is going to create the circumference of the circle, that's going to be r 2 pi r. And the circumference on here is going to be 4x. So I know that 2 pi r plus 4x needs to equal 4 feet. Now, that's not what he's going to minimize. That's one of our constraints. That is a constraint equation. Constraint. There we go. That's our constraint equation. And it actually has an r and an x in it. I don't know if that's going to matter. It says they want you to maximize the total area. So if you're maximizing the total area is going to be pi r squared plus x squared, because it's going to be the area of the circle plus the area of the square. So that area is what we want to maximize. And so that's what we're going to be taking the derivative of. So you have to figure out what equation is going to be the one that helps you, that you're going to need to maximize or minimize. That's the one that you're going to be taking the derivative of. I don't want to take the derivative when I've got 1, 2, 3 unknowns. So I'm going to use my constraint equation to make it so that I only have 2 unknowns here. And so what I did was I said that 2 pi r was 4 minus 4x, and I said that r was equal to 4 minus 4x all over 2 pi. And so I came over here and I said 4 minus 4x over 2 pi squared, pi r squared plus x squared is my a, and that would be my a in terms of x. That's like my function. And so then I have my pi times, this is going to be 16 minus, I've got 4 times negative 4x would be a negative 16x, and another negative 16x gives me a negative 32x, and a positive 16x squared over 4 pi squared plus x squared equals your a of x. One of these pi's can go away with one of those, okay? And I factored my 1 over pi out, and then I made like 16 divided by 4 is 4. 32x divided by 4, I made that 8x. And then 16x squared divided by 4, I made that 4x squared. And so, next thing, I went ahead and, since I wanted them all to be the 1 over pi here, I went ahead and multiplied that one by pi over pi and got my pi x squared. Okay? So now, derivative. We've got our 1 over pi times our derivative here. And what do we have? Well, we have negative 8 plus 8x plus 2 pi x. And I can factor a 2 out. And I've got negative 4 plus 4x plus pi x. And I can set just this piece equal to 0. because I want, this is my derivative, but I want to see what makes my derivative 0 and what makes it 0, because this can never be 0, right? 2 over pi can never be 0, but this could be 0. So now I'm going to add 4 to both sides because I'm moving that 4 over. I'm going to factor an x out. And then I'm going to divide by that 4 plus pi. And then see what that equivalency is. When I put it in my calculator, it's roughly 0.560. And we need to check our endpoints on this one, because we had that constraint that it had to be 4 feet. So we just want to make sure, and we also want to make sure that we are looking at a maximum. This one, you just got to figure out. So if I put a half in to my derivative, I'm going to get 4 plus pi minus 8. I'm going to get a negative value. And then if I put like 1 in, I'm going to get 0 there. I'm going to get 2 pi. I'm going to get a positive value. This is actually your minimum. Ooh. And we're looking for, come on, pen. We are looking for maximizing our total area. So therefore, we need to figure out what are my endpoints here? Because right here, that if you didn't make a circle at all, your x would be 1, because 4 times 1 would be 4. So x would be like 1 foot. So your x has to lie between 0 and 1. So we're going to try a of 0, and we're going to try a of 1. And I mean, while we're there, we can just make sure that this is a minimum. But we want to look at all these things. So if I put 0 into my area equation for x, let's find it before I took the derivative here. There's the one before I took the derivative, so I'll be using that one. And if I put 0 in, it zeroes out everything with an x, and I get 4 over pi, which is approximately 1.273. And if I put a 0.560 in, I get approximately 0.560. And then if I put in a 1, I'm going to get, this is negative 4 plus 4. I'm going to get 1, because I got pi over pi. So which one is the maximum? This one is the maximum. So if the length of the square is 0, area is maximized. Therefore, the total area will be maximized if Justin uses all the wire to create a circle. This is an endpoint maximum. Doesn't really happen that often, but that's why I've been having you make this chart every single time. And we did have to think about that because it's like, oh, he wants to make a circle and a square. We're going to use, I ended up solving for x. And so it ended up giving us that the only way he could do it, or for the maximum way would be to not have the square at all, okay? So you do need to start, kind of just keep in mind that things like that can happen. They don't happen very often. And I should have had equal